Good afternoon, everyone. My name is Joe Steele. I'm the Senior Communications Director and Director of Legislative Affairs here with LIFT. Thank you so much for taking time to join us today for another edition of our Liftoff webinar series. We're looking forward to hearing from NADCA today, Paul and Steve, about trends in high pressure die casting and lightweight die casting or die cast structural components. Certainly appreciate their membership with LIFT, and we appreciate everyone taking time to join us today. A few housekeeping items for you before we get started. We do have a full house, so I encourage everyone to put their phones or computers on mute so we can avoid any background noises during the presentation. We are also recording the presentation, so that will avoid any background noise in the recording as well. Our webinar today will be posted on our website at lift.technology later on today, or certainly by tomorrow morning, so you can revisit it then or share it with any folks who you think might be interested in the presentation today or who may have missed it for one reason or another. We do ask that you do submit questions. You can do so via the Q&A function that we're all familiar with in these still virtual times using the Zoom platform and other platforms. So go ahead and fire off a question using the Q&A function, and we will facilitate the Q&A after the presentation today. We'll reserve a little bit of time afterwards to do just that. I do want to spend a little bit of time to share with you about LIFT. For those who may not know who we are or what we do, LIFT is one of 16 National Manufacturing Innovation Institutes. We are a public-private partnership between the Department of Defense, industry, and academia. We are a Department of Defense sponsored Manufacturing Innovation Institute based here in Detroit. We're a nonprofit 501c3 public-private partnership whose goal is to drive American manufacturing into the future through technology and talent development. We believe the future rests on smarter manufacturing, and that includes their national economic security and resiliency. And the next area, the next region that tackles smarter manufacturing and masters smarter manufacturing first will come out ahead, and we want that to be the USA. So what do we mean by smarter manufacturing? We really mean the connection between materials, processes, systems, and talent. And I know we'll hear some of the materials and processing today from Paul and Steve at the NADCA team, but that's what we're talking about. We're looking at manufacturing holistically. So we do that through our two programs at LIFT, Leading Innovations for Tomorrow, our technology program, and Learning Innovations for Tomorrow, which is our talent program. I'll give you a little bit of information on each of those. Leading Innovations for Tomorrow, you see on our screen are four really pillars of technology, or pillars of technology focus area, everything from integrated computational materials engineering to agile and smarter manufacturing, advanced alloy process development, multi-material joining. And you can see on the screen here, I won't get into each of these, but these are, deeper dives into each of those pillars and kind of where we and our ecosystem operates. So we invite you to come to our facility when it's safe to do so, visit with our technicians, reach out to us and talk to our engineers, learn about what we're doing here, and to really take innovations from research across the Valley of Death and into commercialization. On the talent side, Learning Innovations for Tomorrow, it's still about innovation and new learning tools, pathways, and venues. Revolves around our Ignite Mastering Manufacturing curriculum available for high school students in our Learning Lab and around the country. You see the Learning Lab photo there. It's perched above our high bay, where before the pandemic, we had about 120 students each and every day coming to participate in our facility and in our Ignite curriculum. We're also offering world-class certification programs, welding, CNC, industrial technology maintenance, and robotics, both through our LIFT certified program and Operation Next program, which is growing beyond just a military program where we're supporting or separating men and women from the military, providing them opportunities to earn credentials before they leave the service. We're piloting that in industry right now in a response to the pandemic. So continuing to train and educate folks going forward. So I mentioned we are a membership organization, nonprofit 501c3 based here in Detroit. So what do members get from becoming a Lyft member? Well, everything here on the screen. I won't get into each of those today, as I know we want to get into the presentation, but we'd be happy to talk to you about any of those, from our trusted advisorship to our technology and talent development, our showcase, which I hope you guys can come visit soon in Detroit, connecting. But we are here to connect and convene. So thank you very much for joining us today. Please reach out to us with any questions. Please shoot a Q&A during the presentation, and I'm going to stop sharing. And I am going to hand the presentation over to Steve Uvardi and Paul over at Paul Brenkleon at NADCA. So Paul and Steve, the show is yours.
Okay, Paul will be providing the presentation. This is Steve. Just wanted to thank Lyft. We NADCA are proud members of the Lyft organization, and appreciate the opportunity to provide the presentation that will now be delivered by Paul. We'll be happy to answer any questions at the end of the session here today. Appreciate everybody's attendance. Hope everybody walks away with having learned a little bit of something, or being enlightened a bit on structural die casting. So with that, Paul, take it away.
Thank you, Steve. My name is Paul Brenkleon. I'm the Director of Research, Education, Technology here at the North American Die Casting Association. Today, my outline, what I'm going to review is why do we have to have structural die castings? What's driving the need for structural die castings in the industry? I'm going to talk about some examples of those structural die castings, some applications and specific castings. And then when we're looking at structural die castings, one of the benefits is in joining operations, in hooking those castings up to other components. So the need for die castings, for structural die castings, it comes from several sources. One is going to be just the lightweighting and aluminum content. We can see on a graph like this from Ducker is the amount of aluminum in vehicles ever increasing past 2020, 2021, all the way to 2028. So castings are necessary in making vehicles lighter. So we see that aluminum content increasing, and then we see that aluminum content in various structural components inside the vehicle. And then within that, we also have CAFE targets. So those CAFE targets are requirements from summits or from legislation that happened in 2012 in increasing the miles per gallon of the entire fleet. So in reaching those targets, those CAFE targets, they've got to make the vehicles lighter. So we have the aluminum content increasing. We got the vehicle, getting lighter and lighter, but the strength and durability and reliability of the vehicle in a crash environment still has to take place. So with that, we have an overall reduction in mass of 7% is the target by 2028. So this is going back to that number of pounds in a vehicle, pounds of aluminum. And we can see where that's coming from. So it's coming from, the engine, transmission parts, brakes, wheels, and all other components. So within this, we have the structural components, which make up a large majority of growth components in the die casting environment and being applied to vehicles. So it's unclear whether the current administration is really going to take hold of this and how that's going to drive us to 2025. But the past legislation from 2012 is still in place. So that hasn't changed under the previous administration. It's not changed under the current administration. So as we move forward, we have to see these targets, because those CAFE requirements are ever looming, driving us to reduce the weight of the vehicle and increase the miles per gallon of the vehicles. So that's what's kind of driving us forward, making more products into structural die castings. So what is a structural die casting? So I want to get into the process. So when we're talking about structural die castings, we're not just talking about a standard die cast process. We're talking about a die cast process that then has additional parameters and items in that make a structural die casting what it is. So the first is going to be high vacuum. So in a structural casting, we're going to have high vacuum capability, and this type of process needs to be able to achieve a vacuum level of about 50 millibars to 100 millibars. So with that kind of vacuum draw, we're eliminating a lot of the air inside the system. We've got to be able to monitor that and monitor it in real time. So when you're making a die casting, you're injecting the aluminum at high velocity. So you can fill a casting, whether it's 2 pounds or whether it's 75 or 80 pounds, in the time frame of about 49 milliseconds to about 90 to 100 milliseconds. So in 0.1 seconds, we're filling a 70-pound die casting. So that injection speed is very rapid. Solidification takes place very rapidly. So we've got to have systems that are able to monitor and control not only the shot parameters and all the other parameters of the die cast process, but the vacuum systems and humidity control systems or humidity monitoring systems as we inject the aluminum into the die cast machine. So when we produce a casting from a high vacuum process, and we produce a structural casting, these castings have extremely low levels of porosity. These castings can be solution heat treated without blistering. They're weldable. They have good uniform mechanical properties. They have higher strength as compared to standard high pressure die casting. So we get some good mechanical properties, and ultimately they have better elongation. So with that better elongation, their durability in crash tests, in bending instead of breaking and snapping. So we're reaching elongation values of 10 to 12, 15% in some cases. So with that high elongation, we're going to deform the casting and not break the casting in a crash test situation. So why use vacuum die casting? We want to reduce the gases in the shot sleeve. We want to reduce the gases in the cavity and thus reduce porosity levels, improving those mechanical properties, making them heat treatable. We want to have castings with uniform and very small wall thicknesses, meaning 3 to 5 millimeter walls. So we can get the same type of strength, durability, and elongation out of a casting that's got a 5 millimeter wall as it does with a 10 and a 12 millimeter wall. Ultimately, we want to be able to produce these aluminum castings out of various aluminum alloys. So there have been structural alloys that have been developed for the entire process to give us unique properties based on the alloy within this high vacuum process. This is a graph showing the elongation value. So higher elongation over the evacuation level. So we can see that if we don't get good evacuation levels of the gases, so we have low vacuum or vacuum assist, we're going to get lower elongation values, where we can get higher elongation values with very low evacuation. So this is a higher vacuum level. This is a lower vacuum level. And the better we have a vacuum in our molds, the better the elongation from the alloy, plus the individual alloy properties, which we'll talk about in a little bit. So ultimately, we have a die cast process, and this is called a shot profile. So with this shot profile, we're kind of taking a fingerprint of this individual shot that's making an individual die casting. And with this, we have the slow shot injection speed, and then we start the vacuum. We draw the vacuum. By the time we reach the end of slow shot, we've now achieved a 50 millibar to 100 millibar vacuum. It's here. And then we enter into fast shot. We then have to stop the vacuum as we reach the end of shot so that we're not filling the vacuum systems. And then we enter into an intensification phase. So we look at these shot profiles and we can tell whether we're getting a good casting. And then within those shot profiles or those profiles, we can not only measure the vacuum levels and the shot, but we can also measure the humidity levels. So we can actually determine if we have excess humidity creating porosity in the die casting. So we've got to have vacuum systems, runners, lengths, vacuum valves, all capable of removing that air, removing it very rapidly while we're filling the casting to make sure that we have a very tight process. And we then also have the entire tool sealed. The tool has to be clean. It means it can't have any dye lube or any excess liquid inside the machine while we're making the die casting. So this is the moisture in the die. And when we're controlling that moisture, we have the tool completely sealed. So this is a side view cutaway section of a die cast die. This is what we call the cold chamber or the shot sleeve. The metal is put in here, and I'm going to show you this in more detail here in a minute. And then the metal is injected, and this becomes the cavity. We can see all of these seals. So these die seals are necessary if we're going to seal this tool. So when we draw a vacuum, we're not just pulling in outside air and replacing the internal air of the cavity with external air from the outside world. So we've got to have all of the components sealed, the entire tool, and then all the moving components in what we call the ejector half. So these seals are important to keep out moisture. They're important to keep out any air from being drawn into the cavity. This is once again, a fingerprint. This is actually a snapshot of the vacuum system in operation. So here we're not only looking at the humidity level, we're looking at how well we're drawing a vacuum. So we turn the vacuum on, we draw the vacuum down, and we're achieving about 50 millibars in this particular die. And then each one of these is a shot, is a die casting being made. So we're monitoring the vacuum level, and then we're also monitoring the humidity level. And this humidity sensors are located at each vacuum point. Once again, a distinction between structural die casting and vacuum assist or normal die casting is that structural die casting can have multiple vacuum points. So we're going to have 2, 3, 4 vacuums inside of a mold, all drawing vacuum on the same mold, all measuring humidity. So we can see the humidity sensors at each one of the vacuum points, and then we can measure the vacuum level. So here's the different running criteria. Here we're achieving about 120 millibars of vacuum. Once again, much higher than here. And we can see our humidity level is around 90%. If I were to see this, I would then say, I've got a water leak or I've got excess lube. Any humidity of this level is going to create porosity in our castings. And once again, if we can't measure it, we can't control it. So if we're measuring humidity, we can see the difference of 15% to 90%. We're now producing a casting that may have detrimental effects or excessive porosity, giving us blisters and defects. So we can see that this low gas porosity is very key in making good weldable seams and in our joining operations. So we're just showing the difference between different types of vacuum systems. This is a high vacuum system. This is a conventional vacuum system, and this is without any vacuum. We can not only see the type of air that's entrained in the casting, You can see the amount of air in these x-rays. And then these type of conditions are going to give us a good weld seam. So this is actually the weld seam we're looking at, and from the different processes. So here's how the process works. Through the next set of slides, I'm just going to illustrate the process. So we have metal, the red here, indicating the material, the aluminum material. It's entering in what we call a cold chamber or shot sleeve. As it enters into that shot sleeve, it fills that shot sleeve to a level. We call that our fill percentage. We then start the piston forward. This is the injection piston. As the piston covers what we call the pore hole and closes the pore hole, we then turn on the vacuum system. We have a vacuum system on the chamber or the shot sleeve, and then we have a vacuum system in the mold going to vacuum tanks. So we have a large vacuum reservoir that we turned on, and this is now moving forward. The metal is moving forward into the cavity. As we pass this point where the vacuum in the chamber, this vacuum is shut off, and we have these vacuums in the die still on. So we're still drawing vacuum here. This one is turned off. The metal is now entering the cavity shape, fills the entire cavity shape, and then the vacuum system turns off as it reaches the top vacuum point. And there's several ways that's achieved. With that vacuum off, the mold is now filled, the casting solidifies, and we pull the casting out of the mold, and then the process repeats. So that shot fill time, once again, is between 49 milliseconds, 0.049 seconds, to about 0.09 seconds or 90 milliseconds. So very rapid filling. A lot of considerations need to be, we need to take into consideration when we're casting these parts, what kind of machine we're going to cast it in, what's our part, our shot, our die casting machine size, what kind of pumps do we need to evacuate that amount of air. So based on the volume of the casting, so we're making a small casting, we're making a very large casting, and then we have to have this thing sized appropriately to be able to pull all of the air out of the process. And once again, we got to have the shot sleeve evacuation. So here's some valves that are used. These are vacuum valves, and there are several different types of vacuum valves. There are metal front valves. There are poppet valves. So each one of these are different vacuum systems. There are different pistons for injection. There are blocks that are called chill vents that we have vacuums attached to. So all of these are different systems for removing the air from the system, from the die casting. So here's a 2-cavity, 3-plate tool, and it has a vacuum system. So we're injecting the metal in through the center of the casting. Here's another casting. This is the shot. This is the gating system. This is the actual part. And we have 4 vacuum valves coming through chill vents. So these are chill vents, and then each one of these is attached to an individual vacuum. So items that we haven't touched on yet that are very important to the process are product development and simulation. So we simulate this. We use a lot of flow modeling software to determine how the casting is going to fill. Understanding the design and all the components we're using, and making sure that everything is sealed. Because once again, we're drawing a vacuum and all we're doing is pulling air from the outside world, then the high vacuum process is kind of useless. You have to understand our shot end and the capability of the shot end, what type of lubricants we're using to minimize any water or any lubricants in the shot itself. And then we've got to have some sort of thermal control. We utilize that thermal control by using additive manufacturing. So whether we're using additive in a shot block or in a core, we're using additive manufacturing, and we're printing these, and we're actually printing the cooling lines at various shapes and sizes to facilitate the cooling and thermal control inside the casting to eliminate different types of porosity that are going to exist. So examples of die castings that are being used, we've got vehicle castings. So for cars, motorcycle, recreational vehicles, subframes, cross members, engine cradles, door frames, instrument panels, thin walled suspension parts, battery and high voltage housings. So for the EV market, electric rotors, and then there's a multitude of brackets. So this is a list of those castings that are being used, being produced as structural castings today. So some of the advantage of structural castings is that we can take and replace heavier materials. So we can replace stampings and other steel type materials or steel aluminum weldments. We can replace other high cost materials with lower cost, lower weight, thin wall aluminum die castings. So we get better performance and better pressure tight castings with this type of a process. Remember, these castings have high elongation. So in a crash, we're going to see these castings buckle and not break. So these castings have very thin walls. We then integrate several different parts into them, and I'll talk about that in just a moment. These have good mechanical properties, higher than normal die castings, giving us good crash performance. They can be welded, they can be riveted, they're distortion free with tight tolerance, and with some of the alloys that are being developed for structural, they have great corrosion resistance. And then obviously a pressure tightness to them. So here's an example of a Audi B-pillar. And this used to be 8 different parts weighing about 9 pounds, making it into a structural die casting, now weighs about 5 pounds, and it's one casting. So eliminating the assembly operation, eliminating all the other components. Here's a BMW shock tower. Now this was traditionally 5 welded steel stampings, weighing about 18 pounds. As a die casting, it's now 7 pounds, and it's a single piece, so it's 40% lighter than the traditional welded part. Here's an overview of all the different components that are being die cast today as structural die castings. So not only do we have the shock towers and B pillars that I just showed here, we have A pillars, C pillars, inner back hatch, brackets, door structures, cross members and cradles, high voltage battery housings. So all of these are being cast today as structural die casting, replacing other traditional components. The alloys now being used, so this is an Oral 2 alloy. As I mentioned, there are several alloys that have been used for several years, and then there are also alloys in development to enhance the properties of structural die castings. So here's 2 different alloys. This is a Castasil 37 made by Rheinfelden and a Silifant 36. Both structural die castings replacing stampings. We have a BMW convertible front end made of Silifant 36, and then we have it in the F temper. So these die castings have the ability to be T7 heat treated, T6 heat treated, or with the alloy development, having no heat treat and still getting good mechanical properties because of the process. Other castings that are being done today are engine cradles made of a Silifant 36 and an engine base bracket made by Honda. And as I mentioned, battery trays. These battery trays are coming in various shapes and sizes. And in today's world, like what Tesla is doing, they're now integrating the battery tray as part of the structure of the car. So it's not just a component that's sitting in the car, it's now going to become part of the structure of the vehicle. So this becomes part of the frame, and the batteries then lay inside that framed structure. Now, Speaking about Tesla, one of the things and developments that have happened just in the recent past, in the past couple of years, is the size of the machines are ever increasing. So this is a 6,100 ton die-cast machine. So just to give you an example of the size of that, you can see a man standing here, and he's barely coming up to what we call the shoe of the die-cast machine. So this is a 6,100 ton. Tesla's named it the Giga Press. And with that, they're making the rear end and as an entire single die casting of a vehicle. This is a YouTube video. Anybody wants to see this, this is really unique, what Tesla's doing. And you can go out to this. You can see this, you can write this down, get this video, or go out there and Google the 6,100 ton machine at Tesla. This video will come up on YouTube. Very unique video. One of the things that Tesla has done is they have reduced a single casting that they're making in production on this Giga machine. It went from 79 individual castings to one single die casting, saving them between 100 and 150,000 square foot of assembly space. So it's not only the assembly time that's being saved, it's the floor space for assembly and the production by combining 79 different parts into a single die casting. The alloys that are being used, this is the chemistry of the alloys. So we've got several different types of alloys here. These are the alloy designations. And then we have the chemistry: silicon, iron, copper, manganese, magnesium, strontium, and then the different heat treatment, a T5 heat treatment, T6 heat treatment. What I've outlined here are the iron and manganese levels, because in these alloys, we're maintaining silicon levels to give us good fluidity, but then we're dropping the iron level and controlling the manganese to give us castings that are less brittle and higher elongation alloys. So with these alloys, we have the iron and the manganese combining to enhance the die life. We're adding magnesium for strengthening, and strontium is being added at certain levels for silicon modification. So we're modifying the silicon in the aluminum from a needle-like structure to more of a nodular structure. So these are some of the alloys that I mentioned just a few minutes ago in some of those applications: Silifont 36, Cassis 37, Oral 2, Oral 3, Oral 5. So we can see these alloys all have that silicon range anywhere from 7% all the way up to about 11 or 12%. They're controlling the iron and the manganese, very low iron levels, 0.15, 0.25, 0.13. Controlling the manganese levels, very low copper. I mentioned that these have great corrosion resistance because we're limiting the amount of copper in these alloys, adding in magnesium for strengthening, and then modifiers like strontium to help modify the alloy to give us good fluidity while we're filling those castings. This is just an example of these alloys and their tensile, yield, and elongation. And I just want to point out that elongation levels on some of these alloys can reach as high as 18% and not see a reduction in tensile or yield, or a dramatic reduction. Some of these alloys can be made so that they have very high tensile and yield and low elongation. So we're approaching iron forgings as far as the ability for tensile and yield of these type of alloys. Other applications are in the trucking industry, so heavy trucks using a Silifont 36, using motorcycle frames for a Yamaha. So these are structural die castings and seat cradles, rear forks, all structural die castings for the motorcycle industry, for motorbikes for Yamaha and seat frames, and then parts for snowmobiles. So these parts are reaching across various industries, replacing, heavier components or multiple components into a single die casting. When we're looking at these castings, we have to use joining operations to bring them together with other components. So we use riveting, spot welds, clinching, MIG welding, laser weld, all different processes for bringing together these components. One of the projects that NADCA is working on is riveting. and so we're working with Volhoff, a company, to help us further develop the riveting of aluminum castings. So riveting is been there for many years, and we're looking at improving that. So the riveting of these type of structural alloys is more uniform, more reliable. So we can see a component like the Ford 150 has, between 2,200 and 2,700 rivets that join all the different aluminum components together. Along with riveting, the other joining methods are welding. So we're welding high vacuum, high pressure die castings together. So in the past, when you try to weld just a standard die casting, that weld is going to fail. It's not going to give us a good weld. In this case, we're now welding different die castings, 2 different die castings, or we're welding die castings. So this piece, and this piece are die castings, and we're welding those to different types of materials. So we've got either hydroform or extruded aluminum that's being welded to a die casting here and a die casting here. So in general, the automotive market is the largest, and biggest growth market for high vacuum, high integrity die castings. It's mainly driven by those CAFE standards and emission standards. So we've got to make cars lighter to give us better fuel economy. We're going to be able to do that by replacing heavier steel components with aluminum components, as long as those aluminum components can meet the same performance requirements as the components they're replacing. Other markets are motorcycles, recreational vehicles, boats, trucks, and other niche markets. For the automotive products, we're seeing these machines get larger and larger and larger. So most structural die castings are made today in 2,500 ton, 3,500 ton, 4,400 ton die cast machines, very large die cast machines. We've seen pictures of the 6,100 ton, Tesla's calling the Giga machine. And I know that there are several more of those machines that are on order to go into the industry because they can make much larger castings using the same structural process. So the value added by combining these castings, far exceeds traditional die castings and far exceeds all the other components. So making 79 parts into one single die casting. So every 3 to 5 minutes, you're getting a part out that doesn't have to be assembled, doesn't take up that additional floor space, and still meets the performance requirements of all those other components, is what structural die castings can do for us today. We just need to understand that when we're quoting this, when we're casting these parts, we can't underestimate potential scrap in the system, and that we have to take into effect that this process is very tightly controlled. Any kind of variation in this process is going to create scrap. So we can't underestimate what we need to do and the process control we need to be able to make a high vacuum structural die casting. So This is a fast growing segment of the die casting industry, along with the electrification of vehicles. This is going to add additional opportunity to other die cast manufacturers. So we're going to, once again, we're going to see lighter vehicles. We're going to see more castings come from other components and be made into structural castings. So more programs are going into this, and the supply base is still growing. So if you want to learn more about this, NADCA has several publications on the standards for high integrity and structural die casting processes, product standards for semi-solid and squeeze casting. We've got books on high integrity aluminum die castings and then high integrity castings. So several different resources that you can use to enhance your knowledge or your understanding of the structural market, capabilities of that market, and the capabilities of those individual alloys with this type of a process. I want to thank everybody for coming today, and I want to open this up to questions for either Steve or myself to answer.
Awesome. Thank you very much, Paul. Again, this is Joe Steele back here with Lift. Thank you very much for the presentation. Hopefully everyone on the call today understands, how NADCA fits into the Lift ecosystem, particularly as we're talking about materials and processes. You can absolutely see why they're such a valued member here through the presentation today. So we did have a number of questions come through. If you do have a question, please use the Q&A function. We're happy to facilitate those. If we don't get a chance to answer your question here live online, we'll be sure to pass those questions along to Steve and to Paul. And I encourage you to reach out to them directly via their email addresses and phone numbers you see on the screen here as well. So I'll try to go through a couple of these questions as fast as we can here in the time that we have left. So Paul, you talked about this is a growing industry. The vacuum die casting is a growing industry. Can you ballpark how common it is across the industry?
Well, there are a lot of die casters that have been around for a long time that are now making structural components. There are die casters that have developed specific facilities just for making structural components. So common, I want to say it's out there. It's not as prevalent as standard high pressure die casting, but it is growing. So it is throughout the market, and die casters that make normal everyday die castings and die casters that are making the same die caster could also have a facility that's making structural components. So common in the sense that the die casters are evolving or growing into this market and adding the resources to be able to do this.
Now you talked, I know, about some of the aluminum involved in structural casting. Someone commented that magnesium does not require vacuum to achieve similar results. Can you comment on that at all?
Structural magnesium is a difficult thing in the sense of you're still magnesium die casting has to have extremely fast fill times, and it comes down to the alloys that they're casting for structural magnesium. It does not have to have the same vacuum systems, but it does have to have a shot end on the die cast machine that frankly outperforms an aluminum die cast machine, because you have to have extremely fast fill times, because you have extremely fast solidification times in the magnesium process. So although it doesn't require vacuum, it does require a process that still has to be controlled and must have extremely fast fill times. Got
it. So these questions were coming in throughout the presentation, obviously. So we have to go back in time for a couple of these. But you were talking about the humidity levels and the difference that the levels can have, or the impact that the different levels of humidity can have. Is there such a thing as an ideal humidity level?
Well, as I was making structural parts, we wanted to maintain anywhere from 10 to 25, maybe 30%. Once we got in that 40% range, we started having porosity issues due to the humidity in the mold. So 30% or less, we would make the die castings. Anything greater than that, we would shut the process down, determine where the fluid was coming from. So higher humidity isn't just humidity as we feel in the world of humidity. It's actually fluids that are leaking into our mold, into our process from some point.
There are a couple questions I think we should probably take. We can take offline about where folks can purchase some of these alloys, and if they're major suppliers, they can reach out to. But I want to go back in time a little bit further. Can you go a little bit explanation? You may not, I don't know if you need to go back to the slide, but do you need to go? But can you explain a little bit about the 3-plate tool and exactly what that is?
A 3-plate die, a standard die cast die, fills metal from the front of the tool into what we call a biscuit and a runner. A 3-plate die actually fills the metal from one plate back, and it actually comes up and then fills through the center of the mold, like a hot runner in plastics or a hot runner in zinc. And it takes 3 plates to make that work, because the mold opens up and then the 2 plates separate, breaking apart the runner system from the feed system or the gating system on the mold. So it's about a die design. NADCA has some books and publications on 3-plate tooling and the actual applications of 3-plate dies.
Excellent, thank you. Is there what is the best alloy for corrosion resistance, but also structural?
Well, because these alloys all have extremely low copper, they all have better corrosion resistance than like a A380 or an A360 alloy. So A380 is probably the most common die cast alloy cast today in all die casting. So we have A380, A360. Both of those have higher copper levels. The structural alloys all have very low copper levels. So Oral 2, Oral 5, I've personally done some corrosion resistance on, very good performance as compared to standard die castings. So what's the best one out there? I'm not going to say which is the best, but I can tell you that they all do outperform standard die castings when we're looking at no coatings and structural, strictly the corrosion resistance.
Within the standard alloys, outside of the chemistries for the specific structural die casting alloys, the best common alloy would be 518. It's not overly casting friendly because of the low mag, but it does have very low copper, as Paul has mentioned. So probably 518 followed by an A360 would be the choices for standard high pressure die cast corrosion resistant alloys.
And I agree with that, Steve. I think A518 is an aluminum mag alloy, whereas 360 and 380 are aluminum silicon alloys.
Yep.
So they have slightly different structure, but 518 is a very good standard die cast alloy that has great corrosion resistance. Tough to cast, but good corrosion resistance.
So we're talking about corrosion resistance. What about the fatigue properties? You talked about improved porosity, but there's a comment here about oxide films would still be expected.
Well, oxide films, you're going to have some oxides inside of a die casting because of the ladling process. But with structural die casting, they're using a feed system that limits the amount of air exposure. So we get less oxide films in structural die castings than normal, but they're still going to be there. So as far as fatigue, I don't have that data in front of me to tell you what's better for fatigue. With high elongation that the structural alloys give you, they should perform better in a fatigue situation. because of that elongation, but I don't have any of that data in front of me.
Couple of questions on the humidity piece. What provides instrumentation for measuring the humidity in the tool?
So we have humidity sensors, and they're built right into the vacuum system. So as we're drawing air out of the vacuum, out of the mold through multiple vacuum points, then we have humidity sensors right there in line with that. It's measuring the humidity of that air, and it's a standard humidity device. I would recommend, contacting one of the vacuum companies that are supplying the vacuum to the die casting industry. And for someone has a question, once again, my email's up on the screen. You can email me and I can then get you in contact with those individuals, give you that type of hardware.
Yeah, we still have a good number of questions. Again, good reminder for everybody. Please reach out to Steve and Paul directly. If we don't get to your question, we'll also share all these questions with them so they can follow up afterwards as well. While we were talking about the humidity, there's a question about if moisture is critical, is there research into regaining visibility for dry lubrication?
Dry lubes are used when the die caster has great thermal control. So there are basically 3 or 4 different types of lubes used. There's water-based lubes, and they're mixed at some dilution ratio. There are dry lubes, and they can be put on electrostatically onto the mold. There are oil lubes that are also sprayed onto the mold. With oil lubes and electrostatic lubes, they're going to give you less porosity concerns, but they require great thermal control, meaning that all the heat that's going to be removed has to be removed from internal to the die cast die. If we have any hot spots or any areas of the mold there that cooling was not adequately designed, then you're going to create hot spots in the casting. We call that then leads to soldering or tearing or some die cast defects due to those hot areas. So there is work being done by the lube manufacturers for electrostatic lubes, for oil lubes, for dry lube applications. But the die design has to be critically done if that's going to be what's going to be used. Or there are coatings. There are coatings that are being used on the mold faces that will also help in release of the casting and less lube on the mold.
We have time for a few more, I think, with a couple of minutes left. I want to be cognizant of everyone's times. We're talking about electric motors with integrated power electronics that cause heat. How thin can you reliably and repeatably vacuum die cast aluminum fins?
Probably reliably 3 millimeters. You can get them smaller, and there are die casters today that cast aluminum around 2 millimeters in thickness. Magnesium can be somewhat thinner, around 1 millimeter, 1.8 to 2 millimeters reliably. Zinc, there are high fluidity alloys that can cast reliably at 10 thousandths in thickness. So aluminum, a good fillable area of a die casting is going to be right around 3 millimeters for these type of castings.
But for fins, that is somewhat contingent upon the exact configuration of the fin, how much draft angle is present, and I think the answer there is to deal directly with the caster that's familiar with the configuration, or certainly review the overall design prior to cutting the thickness, length, and depth of the fins in stone. But yeah, certainly two, and on certain cases, below 2 millimeters would, I think, be achievable.
Most of the current structural die casting addresses the auto market, probably due to volumes, is suggested here. Are there similar trends being seen in commercial vehicle industry? You know, due to with lower volumes?
I think so. I think we're now seeing, you know, electric trucks, electric, you know, other type larger vehicles. I do know that structural die castings are now being used, as I pointed out. I had one example of structural being put on large semi-type trucks, and those are now replacing heavier components. So the commercial industry, the recreation industry are now starting to take advantage of structural die casting also.
Excellent. There are a couple of more questions, but we are going to have to pass on those to be cognizant of everyone's time. I do want to thank everyone for joining us today. Encourage you to keep joining our webinars. Want to thank Steve and Paul from NADCA. Thank you for your membership in Lyft. Thank you for your presentation today. We certainly appreciate that. Also want to thank everyone for taking time to join us today. Again, stay tuned for your to your emails. We have another webinar coming up next Thursday after the long holiday weekend with our member CompuTherm, and then the following Thursday we'll be talking about welding with TWI from across the pond over in England. So thank you so much, everyone, for joining us today. Again, thank you, Steve and Paul, and stay safe, and we'll see you next time.